righty, folks. We're going to do number 2. I'll broadcast out in a windowed format. Should have come up as a window to you. Yes? No? Yeah? Alrighty. So that 30 minutes, 30 seconds of nothing was maybe useful. So force exerted by a shot putter on 7 kilogram shot. Shot moves through distance of this and released with the speed of this. So first, I would like to know what the acceleration of the shot needs to be. So I'm going to use V final squared equals V initial squared plus 2A delta D. 2.6 meters per second squared equals 2A 3 meters. A equals something around 2. Squared divided by 6. 1.12667 meters per second squared. Sum of the forces equals MA. F equals 7.0 kilograms times 1.12667. 7.89. That should be it. Sounds good. All right, so number 9. I think the key understanding in number 9 is that your net force and your acceleration have to be in the same direction. If you have that understanding, 9 is a lot simpler than you would think. So I'm going to start off by drawing my force diagram, and I know my 2 forces, Ft and Mg, add up to my net force, because they're the only 2 forces on there, so they have to add up to the net. If I didn't know the acceleration was horizontal, I wouldn't know what direction that net force pointed in, because I don't know the values of those 2 things. But because my acceleration is horizontal, my net force must be horizontal. So if I take Ft and I add it to Mg, they combine, if I had drawn decently, to be a horizontal force, which I'm going to call F net. I know this angle is theta, right? F net is also MA, right? And yeah. So I can say that tan of theta equals opposite MA over adjacent MG. So G tan theta equals A. And I know the time, so now that I know A, how come I know G? Because I'm assuming the only planet that they have planes on is Earth. So I'm pretty safe to assume that this is happening on Earth. So now I can use that V final equals V initial plus A delta T. I have A, T, they tell me V initial is 0. So I start from rest, and I can find my V final. So all from that fact that the acceleration and the net force have to be going in the same direction. That was the key to being able to do that one. All right, number 8. The key to this one, which makes it actually a little less realistic problem, is this designed to support an equal fraction of Tom's weight. So they wouldn't actually be designed that way. And it's interesting, if you look at the picture, you can see they've used the thickest members for at A because they would have the highest one. They'd have a different amount of weight. Oh no, those are frame members. Sorry, never mind. The C is actually going to have the highest force in it. But what this tells you is the Y component is 1/6 his weight for each. So in rope A, you know that so for A, it's 1/6 of 72 kilograms times 9.81 newtons per kilogram. Right? Fixed ropes, right? Yep. Okay. I'm not getting any response. For B, the force of tension B is in that direction. It's going to have two components, with this angle being 30. This component we know is 1/6 mg. So you can say that cosine of 30 equals 1/6 mg over FTB. Solve for FTB. And then for C, same triangle really, except 60 in here. And FTC. And then just do the same. All right? Does that work? Excellent. All right, so number 4. Unfreeze my screen. So I would definitely start by the diagram, weight down, force and tension up, acceleration up. Newton's second law. I'm going to go down as negative, okay? All right, can drop all my vector symbols, right? Because I'm taking into account the directionalities, right? Well, because I made up positive, so the acceleration I made positive and the tension I made positive, so no need for vector. I've taken into account the direction, and the FT I made negative. That's how I transition from vector notation to now only worrying about the magnitude, because the directions I've counted in. So I'm still dealing with vectors. I'm just expressing their directionality because they're linear through positive and negative. Okay. So FT minus mg over m equals a. Substitute in 21 newtons minus 20, 30 kilograms, 9.81 newtons per kilogram equals A. Neither. Neither. So you guys, okay. So you guys are okay with once it hits, then it going off and you figuring it out from there. But you're having a hard time, how fast is it accelerating before that? Well, what's going to happen here is when this is released, MB is going to hit the ground, and MA, as soon as MB hits the ground, the tension falls to 0. Because MB has inertia, it's going to continue upwards just like the projectile. Okay. So what we're interested in is what acceleration does it have as an Atwood machine when it's released. Which is good because we've got a couple labs to do about Atwood machines. Right? Oh, you guys didn't study Atwood machines last year? I know Jason did. Atwood machines. This is an Atwood machine. Yes. Developed by Professor Atwood to be able to study lower rate acceleration, constant accelerations. So by the ratio of the masses hung on either side of this frictionless light pulley, you can have a constant acceleration lower than g. Thus, you can take measurements, especially when you're using something like a hourglass to measure your time, to better see how acceleration is affecting linear motion. So hence, these are called Atwood machines. We do modified Atwood machines a lot of times where we have and I know you did these last year, where you had a cart on the track over a pulley to a hanging weight. Yeah, it looks kind of like, not that, kind of like that. That would be called a modified Atwood machine. So, there we go, a little dissertation on Atwood machines. You'll read an article when we do our variable mass Atwood machine here right after Thanksgiving. An article to read about Atwood. So, give you a little better historical comp. So, MA is going to go up 1.8 meters and then turn into a projectile. Because it is rigidly connected to B, and B is going to go down 1.8. At that point, it becomes a projectile. So we need to know the velocity at that point. Therefore, we need to know the acceleration during that 1.8 meters to be able to find its launch velocity. Huh? Well, we're going to look at the dynamics of it and then look at the kinematics of it. The dynamics of it is how is it accelerating during this time? And that's going to be controlled by the acceleration of the system. Okay? So, I could draw a free body of MA should have FGA, FT, and acceleration. problem is I don't know FT, right? And I don't know A. And I get unhappy if I have two unknowns. So instead, I'm going to draw a free body of the system. And I'm going to draw it like this. Because working around the idea of the turning a corner on the pulley sometimes screws my mind. So this direction for me is clockwise in my little free body diagram up here. Okay? So I've got a force on this way of Fg for A, and a force this way of Fg for B. My inertia is ma plus mb, and my whole thing is accelerating in that direction. Now, for me, that free body helps me see it, but I know it's hard to translate the first time you see it. What I've done is because clockwise and counterclockwise can be thought of as linear directions, I've taken everything that pointed clockwise and said that's going to point to the right. Because if I drew it on the diagram here without doing that, I would have these two forces, FGB and FGA, and I'd have an acceleration that went like this. And a lot of times people have a hard time seeing these two forces as pointing in opposite directions. So what I do, kind of in my mind, I straighten it out, and then it's clear to me that they're pulling in opposite directions. Okay? Now I just do sum of the forces equals MA. I'm going to take A as positive, so I have negative FGA plus FGB equals MA plus MB times A. I know everything, right? MA, negative MAG plus MA MB sorry, all over MA plus MB equals A. And solve for A. Do you want me to go through the kinematics too? Let me know if you do.